So welcome back. So what we have now is we need to try and, I want to develop an equation which will tell me the shape of a wave sometime in the future. And the shape of the wave is determined by what's its y value for a given x value, yeah? Well, that's going to change in time, because that's the wave moves, yeah? So I've got two variables, an x variable and a t variable. And I'm going to be dealing with sine and cosine shapes. But so we can see better, I'm going to draw this as a wave pulse. And you can't see any of that. So I'm going to draw this as a wave pulse. So here's my diagram. It's got the original wave pulse when time equals 0. So sorry, I need to go back here and get my pen. And then I need to go back here. So when time equals 0, it looked like this. And then a bit later, it's moved, so it's there. And a bit later, it's moved, it's there. So the question is, what will the y value be at some given value of x and at some time in the future? You know, this is time going that way. This is x position going that way. That's the game we're going to play. And I know mathematically I can say, well, my y value is going to be some function. Don't know what it is, but some function, and it'll depend upon x for sure. And it'll also depend upon t. Now, people usually feel a bit uncomfortable by two things. One is, why is there a v there? I mean, what's going on with this? And I'll remind you about your dimensional analysis from Physics 1, or your units, if you like. You know, what's on the left-hand side of an equation has to equal what's on the right-hand side of an equation, including the dimensions or units. So if I have meters on the left-hand side, and that's going to equal some function of a thing that has meters in it, that's the x. Minus, in this case, a function of something which has meters in it, and time does not have meters in it. So what can I multiply time by to leave behind meters? So yeah, multiply meters, multiply time by meters per second, and you get meters. So it's a hand-waving argument for why that v's there, but it makes sense from a dimensions point of view. The second thing is, why is it that that negative sign is there? And that's what my wife would call foreshadowing. My wife likes to watch all these like really gruesome cop shows, and she's amazing at predicting what's going to happen next. I can predict sarcastic comments by the cops. I always know what they're going to say, but I have no idea what's going to happen next. And she always knows. And I was saying to her, quit. You know, the University of South Florida doesn't pay you enough. Just quit and write these things. You kind of like know what's going on. She goes, no, it's like, I'm an English major. Originally she was an English major. She goes, and they just drill into you foreshadowing. So when you see the person eating an apple for no apparent reason, you know the body's going to be found in an orchard. You know, that's foreshadowing, you know. So she said they were trained in foreshadowing, so they write with foreshadowing, and I was trained with foreshadowing, so I understand foreshadowing. You know, it's like, I didn't get trained in any of it, so I'm always amazed all the time. Where did that come from? So I'm trying to foreshadow here. I want you to kind of go, why is there a negative sign there? And I'm going to say, funny you should ask that. But here's the thing. When the wave is going to the right, that has to be a negative sign. If the wave were going to the left, that has to be a positive sign. And that might seem really strange. Why would you have a negative sign for something that's traveling in a positive direction? If you think about it, what I'm saying is, I know the shape of the wave at the start, and as time passes, it's going to move in this direction. It's going to the right. Agreed? And in the future, well, I can see the future. I can see what's coming in my direction by looking to where it is now. So if if traffic is flowing to the right, you look to the left to see what's coming. If traffic were flowing to the left, you'd look to the right to see what's coming. When I first moved to the States, I would stand at the side of the road, I'd look in the wrong direction and step out. I'd get to the median and say, oh man, and then I'd look in the wrong direction and step out, because it was so ingrained that you look in that given direction. It took me about 2 months. I'm amazed that I actually survived for 2 months, because I just was so ingrained. But it's the same principle. If you want to know what's going to happen in this equation in the future, look towards the past, if you like. If the thing is moving to the right, look to the left. If the thing is moving to the left, look to the right. So if the thing is moving to the right, look to the left. The VT is like down there. That point there in time will be here. So that's why it's a negative sign, okay? Bit hand waving, but that's okay. Okay, so what we're going to do is we're going to turn around and say, well, let's have this shape, and that's the time c equals 0. We have a certain velocity. If it's traveling to the right, that's a negative sign. If it's traveling to the left, that's a positive sign. And that's the game we're going to play. This is the game we're going to play. I'm going to skip this. I'll come back to it. Okay, so let's do this to a sinusoidal wave, not a pulse, but a sinusoidal wave. So the first thing we have to do is talk about how y varies with the x position. Let's not worry about time. Well, y will be a sine something. It's going to be a sine curve. It's going to be a times the sine of some angle. And this angle is basically, the way you get the angle is you say, well, we want 2 pi radians for 1 cycle. How many cycles is it? How many wavelengths is it till you get to the point of interest? So, well, that's going to be, if it's 9 meters and it's 4 meters wavelength, that's 2 1/4 wavelengths. You've gone down. If it's 12 meters, lost my pen, sorry. If it's 12 meters and it's 4 meters wavelength, that's 3 wavelengths down the road. So this is a really nice way. We just take the ratio of the distance that I want divided by the wavelength, multiply it by the number of radians in 1 wavelength. I have my distance expressed in radians. It's kind of really nice. There's my shape. But I would like to include the effect of time. What does time do? Time takes this point and it effectively moves it, you know, if the wave is going that direction, time takes that point and moves it back in that direction, because later on that point's going to be where you are. So I need to take into account time. This to be a negative sign because it's going in a positive direction. And then I do the same trick. I say, well, let's take my distance that's caused by the motion in time, and let's make it a ratio of the wavelength. So I take my VT and divide it by lambda. And so I get this form. I get y is equal to a sine 2 pi. Let's separate these two guys out. X over lambda minus, oh, sorry, no. So this is an important equation. I actually prefer to write it as y is equal to a sine 2 pi over lambda x minus vt. But it's you know, who cares? It's like, that is all in linear terms. That's in terms of distances and velocities and wavelengths and the like. But let's talk about it in angular terms. So I need to do a bit of substitution here. So I know that my velocity is equal to my wavelength over my period. That's how fast my wave is traveling. And maybe I did need that slide further back. And I also know that my angular wave number, let's remind ourselves, omega equals 2 pi times f. and k is equal to 2 pi times wave number. And so, let's have a look. I've just got to get my thoughts together here. So this v is equal to lambda over t. So that v there can be replaced by lambda over t, and the lambdas cancel. So I get little t over big T, the time divided by the period. Okay? And now I'm going to play with my x. And my x is equal to 2 pi over mu. Did I do that right? Yeah, my k is equal to 2 pi over mu. So, let's have a look. My k is equal to 2 pi mu, which equals 2 pi over my wavelength. Okay? K is equal to 2 pi mu, which equals 2 pi over my wavelength. And there is 2 pi, and there is my wavelength. So I get kx. Final little bit is my period, my omega is equal to 2 pi times f, which equals 2 pi over my t. So 2 pi over t. So substitute for 2 pi over t, I get my omega. So I get the second form of this. They're both the same equation, just in different forms. Y equals a sine kx minus omega t for a wave traveling to the right. Y equals a sine 2 pi over lambda x minus vt for a wave traveling to the right. You need to know those equations. I tend to ask this one more than that one, but that's not a guarantee. That's like, you know, I'm just trying to emphasize to you, I don't want you to blow off the omega and the k version because, you know, man, that's weird stuff. It's actually more, we use it more than the other one, even though it's uncomfortable a little bit. Okay, so let's go back one little bit. So maybe I should have done this beforehand. So I know that my frequency is like how quickly I take steps, and my wavelength is how big my steps are. So my velocity is the product of the two of them. So v equals f lambda is pretty straightforward, yeah? Okay, that's interesting. So student strides with a step size, our wavelength is equal to 2 meters. And a rate, our frequency is equal to 8 hertz. So v equals f lambda. V is equal to 8 times 2, which equals 16 meters per second. Think a hertz has been cycles per second. 1 over seconds is the dimensions, yeah. Fast students, yeah. Okay. So let's try this. Can you ever go this one for me, please? Can you just do this one for me? Actually, no. Yeah, you do this one. I'll do the next. I'm going to put this on pause. Reinforce it. So what I do basically is I've got myself a little diagram. And basically, I just look at my equation. You will not get the equation on the test. You've got to know the equation. But this is just a makeup. So this is like going to be 3 times sine times 2 pi over my wavelength is 2. And then my x, of course, is the position that I'm at, which is 5 minus. And then my vt and my t is 1.2 times, and my v, of course, was 4. So y is equal to 3 sine, those two go away. This is pi, and this is 5 minus 4.8. I think that's right. So y is equal to 3 sine, this is going to be 0.2 pi. So I get my handy dandy little calculator. Remember, you're going to have to use this calculator in the test. So if you're not familiar with it, you might want to get a look at it. It's a TI-30X2S. It cost about $8 or something from, whatever. And basically, we're going to, first of all, check to see what mode it's in. And the nice thing about this calculator is it tells you what mode it's in, and it's in radians for this one. If you're not familiar how to change it, I'll gladly show you how to change it. But basically, we're going to go, it's pretty straightforward, so I'll just go 3 times, it's going to be a sine, and I'm going to put brackets in, 0.2 times pi, bracket, bracket, I get my answer. And I'm getting 1.76 is my answer. And it's going to be in meters. And the answer's there. And if you weren't in radians, I think you get, I can't remember which one it is, you might get minus 2.34 or you get 1.67, I can't remember. But you've got to check to see your units, okay? So not so bad. On this next one, unfamiliar, but basically, let's just picture it. So here's my wave. I have my amplitude, and my amplitude is 4 meters. Wave number, so my angular wave number, which is my k, is equal to 2.3 rad per meter, and my angular frequency is 1.7 rad per second. And then I want to know the y-axis displacement, I don't know what it is. At a position, my x position is 2 meters, and my time is 3.5 seconds. So it's like, I've gone along from the starting point, I've gone to this position, and now I'm going in time along, until I get to that time, that 3.5 seconds. So I say, well, y is equal to a sine kx minus omega t. It's a simpler equation when you think about it. So this is going to be 4 times the sine. K, well, k is 2.3. And x in this case is 2 meters. Minus, it's going to the right, so it's minus. And then I have omega is 1.7. And t is 3.5. Man, I picked some bad numbers for me. That's 4 sine. That's not so bad. That's 4.6 minus. And we can have 1.7 times 3.5. That's going to be 5.95. So y is equal to 4 sine minus 4.6. It's going to be minus 1.35. So now I go clear, and I go 4 times the sine of minus 1.35. Remembering not to use the operator negative, but the actual little sense negative. And so y is equal to minus 3.9 meters. And my answer is somewhere, minus 3.9 meters. Cool. So not bad. You've got to know the equations, know what the symbols stand for. It's not bad. Okay. We're dealing sometimes with linear and sometimes with linear stuff. So we've got to be able to converse between them. I know that v equals f lambda. I'm pretty good at saying f equals 1 over t, so v equals lambda over t is pretty straightforward. I'm not so good at this, but with a little bit of finagling, I can figure out that lambda equals 2 pi over k, and f is equal to omega over 2 pi, and the 2 pi's cancel, so I get v equals omega over k. Okay, we finished now, is that right? So let me just give you a little heads up. All I've done here is I have differentiated the expression I got for the y-axis position. So this is the velocity of that point in time and at an instant, and this is the acceleration. And next time, we'll continue with this, okay? Yeah, next time.